As AI classifiers become more and more powerful, the question begs, who should predict, humans or machines? In our AISTATS2023 paper, myself, Hussein Mozannar, along with a team from MIT and IBM, tried to answer this question in our paper, Who Should Predict? Exact Algorithms for Learning to Defer to Humans. We consider the following scenario. We have a radiologist who, given chest x-rays and medical records, tries to make a diagnosis about the patient. For example, here the patient has pneumothorax. This diagnosis goes to the referring doctor. We can also build very powerful AI classifiers from just the chest x-rays, and they can provide their own diagnosis, which we can then send to the referring doctor. Deferral systems combine humans and AI classifiers by conditionally delegating each example with another AI. This AI model, called the rejector, decides who between the human or the classifier should predict. If the rejector R of x, where x is the x-ray, is 1, we defer to the human. If it is 0, the classifier predicts. The classifier denoted by m of x. It makes a prediction y. Our objective is to minimize the error of our human AI system. We can write down this 0-1 error as the probability that if we defer, that the human is correct, and if we don't defer, that the classifier is correct. How can we learn such a deferral system? The simplest thing we could do is to just threshold the AI classifier's confidence. Meaning, R of x, we defer to the human if and only if our model's confidence is less than some threshold that we can set. However, this can be highly suboptimal. Consider the following figure. We have our AI classifier, which is a half space. The region which it is not very confident on is the region surrounding the boundary, which is colored in green. This is the deferral region. In this region, the AI only makes 3 mistakes. However, the human makes 5 mistakes, 2 more. Because we didn't consider the human's error when we deferred, we can be highly suboptimal. A slightly better approach is to compare AI and human confidence, so that we defer if the model confidence is less than the human's confidence. This can also be so highly suboptimal. Let's consider the following example. The data can be split into 2 groups, blue and red. On the red group, we assume that the human is perfect, while on the blue group, we assume that the human is bad. Ideally, we want to defer to the human on the red group. However, when we fit the classifier without the knowledge of the human's error boundary, we might come up with a classifier that tries to fit the red region instead of the blue separable region. Thus, with this kind of approach, we do not allow the classifier to adapt to the human. Fitting average error is suboptimal in this example. The goal is to jointly learn both the AI classifier and rejector. We want to optimize the classifier to adapt to the human's weaknesses and strength. And we want to learn the rejector to defer between who is more accurate between the human and the classifier. We will see later on that prior approaches for building deferral systems fail in the simple figure that I had drawn in the realizable setting. In fact, we will show that this joint optimization is computationally hard. So let's formalize the picture we had drawn. We will assume that for a given human, there exists linear rejector and a linear classifier that can achieve zero error. So in that picture before, we will defer to the human on the red points, which is now shaded in green, and we're going to learn our classifier on the blue points so that we can achieve zero error. We can show that under this assumption, there exists no polytime algorithm to find linear classifier rejector pair with error better than half minus epsilon unless NP equal RP. Even if the data is not realizable, meaning assumption 1 is violated, learning this linear classifier rejector pair is still hard. In the face of this hardness, we try to come up with an exact algorithm. We derive a mixed integer linear program that can exactly learn the optimal classifier and rejector pair to minimize the 0-1 error of the joint human and AI system. This mixed integer linear program can handle both binary and multi-class problem and can integrate many constraints such as fairness and coverage. However, this linear program has major limitations. It only has a linear parameterization, and it's very expensive to run. It takes a long time. The standard approach in machine learning is to come up with a differentiable surrogate for our true loss function L01, and the standard guarantee that we want the surrogate to satisfy is that of consistency. Well, what is consistency? Consistency tells you that if you optimize your surrogate L over all measurable functions, it will be the same as if you had optimized the 0-1 loss you care about over all measurable functions. It's very important to note that this only holds when you're optimizing over all functions. And in particularly, if we optimize over linear classifiers and linear rejectors, such a consistency guarantee does not give us anything. So it is not enough to get an optimal solution in our linear setting. We will have to come up with a different notion. We will introduce our new surrogate loss, which we dub realizable surrogate. We first define a set of scoring functions, G1 up to GC, for each class in our label set, and an additional scoring function, gbot. We let the classifier be the maximum of the G1 to GC scoring functions, and we defer when gbot is larger than the maximum of G1 to GC. We define this in a probabilistic way by taking a softmax over all of these scoring functions. We can define the probability of deferring as the logit corresponding to gbot. If we write down the log likelihood of our overall system, so let y hat be the system composed of the AI and the human, we can write down this likelihood, and this likelihood will decompose into two terms. When we don't defer, we will have the probability that m of x equal to y. When we defer, by the probability r of x equal to 1, the likelihood will be the probability that the human is equal to the label. If we plug in the parameterization we have above, we derive the following surrogate function. Note that this surrogate function has quite a resemblance with the cross-entropy loss. So let's consider the case on a particular example when the human is incorrect, meaning the indicator that h equal to y is 0. This loss function becomes the same as the cross-entropy loss. However, when the human is correct on a given example, the learner can either decide to defer or to classify and will not be penalized by the choice they make. This surrogate loss satisfies a very interesting notion of consistency, which we will now define. We define a surrogate L to be realizable consistent with respect to a hypothesis class for classifiers M and a hypothesis class for rejectors R, if when there exists a zero-error solution in our hypothesis class, minimizing the surrogate over this hypothesis class will lead to a classifier rejector pair that has zero error with respect to 0-1 loss. So when there exists a human AI team that has zero error in our class, minimizing the surrogate over the class will get us a zero error solution. And we can show that the proposed surrogate is realizable consistent for our 0-1 loss for classes that are closed under scaling and upper bounds the 0-1 loss. This is in contrast with previous approaches. We evaluate our approach on 6 datasets and compare to a set of baselines from the literature. On our GitHub, we provide an easy way to develop new methods and test them on our benchmark. For the setting we have considered in this presentation, that of a realizable setting where there exists linear classifier and linear rejector that achieves zero error, our proposed surrogate and mixed integer linear program can achieve close to 100% accuracy as the data size increases. So on the plot on the right, the y-axis shows test accuracy and the x-axis shows the training data set size. And the different plots correspond to different methods. With red, our realizable surrogate, and black, our mixed integer linear program. And we can see that there's a major gap between our methods and prior approaches, except for one particular method in the literature, which is the mixture of experts approach by Mozannar et al., which achieves good performance on this setting because we can show, in fact, it also satisfies the property of being realizable consistent. However, this surrogate actually suffers quite a whole lot when we optimize in non-realizable settings. In these two figures, we show for two different datasets. One is CFAR 10H, and the other is a chest X-ray dataset. On the y-axis, again, is test accuracy, but on the x-axis is coverage, which is the proportion of time we defer to the AI classifier. So coverage of 0, meaning the human predicts alone. A coverage of 1, meaning the classifier predicts alone. For each method, we can vary the threshold of deferral to plot these curves. And we can see on both of these data sets, our proposed method almost dominates the previous approaches and is competitive over all the coverage region. However, you can see that the mixture of experts approach significantly underperforms the field on these two data sets. To conclude, we studied the computational limits to learning deferral systems. We proposed a mixed integer linear program and a novel surrogate loss and evaluated on real-world datasets. A theoretical open problem from our research is to find a surrogate that is both consistent and realizable consistent. Moreover, we would like to evaluate the approaches on larger dataset sizes for a better evaluation.